Hey guys, it's me. I'm just going to give you guys some notes. This is a topic that can be a little bit more challenging, so I'm going to try to explain it as best as I can, and then if you guys have more questions, let me know. So this is notes 5.4, and what we're doing is we're going to look at the polarity of a molecule, and what that means is a molecule itself can be it's possible to have a molecule have those dipoles, so if you remember, our dipoles are when there's a difference in electronegativity of 0.5 to 2.0, the electrons, if this is, let's say, fluorine with an electronegativity of 4.0, and then let's say this is carbon, which is 2.5. So there's a 1.5 difference, and I'm going to point that dipole towards the fluorine. So those, what I'm drawing right now, these are bond polarity or bond dipoles. But what we're going to talk about is if I were to kind of draw a circle around this whole molecule, is it polar? Does it have an accumulation of negative on one end and positive on the other? So first thing I'm going to do is teach you an analogy that I use. It's going to work probably for some of you and some of you maybe not, but I'll give it to you anyways. So the dog park analogy that I always use is when, like if you have a dog and you take them to the dog park and they're playing with a toy, the toy could be the electrons that are in the bond. And, these two dogs look fairly equal. So they're pulling equally. So this would be our bond. This would be like a fluorine and a fluorine, right? So what happens, though, is that when we have molecules that are not just two elements, that are not linear, for example, this is a tetrahedron, we have all of these dipoles. So we have, whoops, my pen's going crazy. We have the fluorine here pulling on these electrons, this fluorine pulling on the electrons from the carbon, and this one, and this one. So all of this pulling, my dog park analogy is, let's say the carbon is the dog toy, and we have 4 dogs. They're all, some form of a pretty big dog, and they're all pulling equally, which essentially then the toy doesn't go anywhere. So there is no accumulation of charge, which is different than if you all of a sudden throw in a different dog. So if this is not fluorine, and let's say it's hydrogen, let's a little dog now, because hydrogen has an electronegativity of 2.1, and remember carbon's 2.5, so this doesn't even have a bond dipole. So there isn't a way for this to cancel out, so there's going to be more electrons kind of on this end of the molecule. So this will be slightly negative, and then this side of the molecule is going to be slightly positive. Let me show you with the PHET. So the PHET, so this is that first example with carbon and then the 4 fluorines. I'm going to put in the bond dipoles because those are the arrows between the carbon and the fluorine, each of them, and they're always pointing towards the fluorine because that has the higher electronegativity. And another thing, if I push on this electrostatic potential, this is kind of just grayed out, which means that it's not positive or negative. It doesn't have poles. I can also add this, and I don't see a yellow arrow appear. But this will make more sense if I show you another one. So let me show you what would happen if we had, and I'm going to click some of this off again. So here we have, 3 hydrogens, which are, I don't know why the bond dipole doesn't show up very well. You should only have the one bond. Oh, they're drawing them towards the carbon. There's a slight difference in electronegativity, and the FET is set to probably just show any difference in electronegativity with the dipole. But in our learning, we wouldn't draw those. But we would for sure draw this one going from the carbon to the fluorine. And that, because it's not symmetrical, it's not going to cancel out. It's not like 4 equal-sized dogs pulling on something equally so that it doesn't go anywhere. Because of that, we're going to have an accumulation. That gold arrow is telling me it's going to be negative up here if I were to like draw a circle around this, and it'll be positive towards the bottom. And then let me show you, this is, I think, a really good view. So it's red on this end of the molecule, which down here it tells you is negative. So it's a polar molecule. It's negative on one end, positive on the other. So it all depends on the symmetry of the molecule. So here is another, it's a symmetrical tetrahedron. Let me show you, sometimes when you have something that's a not symmetrical shape, like ammonia, if you remember, there's a lone pair of electrons up here, which causes this to be trig pyramidal. And because of that, this is already it's going to be negative up here. So I'll show you, we can put the bond dipoles in. We're going to have this the molecule, that gold arrow is telling me it's negative on this end and positive on this end. And I can show this, it's really red here. And that's because there's a lone pair of electrons sitting right there, which are negative themselves. So let me just kind of keep going through the notes, and then I don't want to make it too long. So when can you cancel out those dipoles? When do the dogs essentially pull at equal strengths, so that the toy doesn't go anywhere? It has to be a symmetrical shape. So it has to be either linear, trig planar, or tetrahedron. And then if it is one of those shapes, then it's possible they're going to cancel, but the atoms going around the central atom, that's what Ca is for, central atom. The ones that go around the central atom have to be the same. And if they are, because these are symmetrical, then they'll be a nonpolar molecule. When you have lone pairs, like I just showed you, you would have a lone pair for a trig pyramidal or a bent shape. They're always going to be polar. Even if there's no dipoles drawn, like here, the nitrogen is here, hydrogen is here. They're only 0.2 difference, so I don't draw the bond dipoles, but because of the lone pair, this is negative partially. This, if I think of the whole molecule, negative partial charge up here, or its pole, and positive here, like our north and south poles on the opposite ends of the Earth. If a molecule is polar, it's negative and positive on opposite ends of the molecule. So this is a chart that I think can really help you to hopefully understand this. So let's say I have water, and water is bent. It has that central atom would be the oxygen, has 2 lone pairs and 2 bonding pairs. So this is a bent shape. So I would just go through these questions. So is this molecule bent or pyramidal? Yeah, it's bent. So I have to go down here. So automatically that molecule is polar. So if it's a bent or a pyramid, because of the lone pairs of electrons, it's going to be negative on that end of the molecule. And there's no symmetry, so it can't cancel. But if you have something that's symmetrical, like let's say you have planar, like boron with chlorine going around, no lone pairs. These chlorines have electrons. So this is 3 bonds, no lone pairs, which is trig planar. So is your molecule bent or pyramidal? No. Is the central atom, which is the B, surrounded by the exact atoms. Yes, the chlorines are all the same thing. So the molecule's nonpolar. This would be one where they would cancel out. Even though there's bond dipoles here, the chlorine is definitely going to be pulling on those electrons. They're going to cancel out essentially. The way I drew it, it doesn't look very symmetrical. But if you remember, the planar is really kind of like that. So it is a symmetrical shape. So I hope that helps you guys, and then you'll be practicing and you can definitely ask me any questions.